Hello everyone. In today's video, we are going to learn about real numbers. So, real numbers are basically rational numbers as well as irrational numbers put together. First, let's see what are rational numbers. The numbers which can be written in the form of p by q, that is, having a numerator as well as the denominator, where the denominator q should not be equal to 0. Such numbers are called rational numbers. The numbers which cannot be represented in the form of p by q, those numbers are called irrational numbers. Now, there are certain numbers which are obviously rational. For example, if you take 2 by 5 or 7 by 3, these numbers have a numerator which is p and a denominator which is q. So, and the denominator is not equal to 0, so we call them as rational numbers. But how about numbers like 5? They are also rational because they can be written as 5 by 1 or even 10 by 2 or 50 by 10. Even such numbers will yield the value 5. So, numbers which can be represented in the form of p by q, which can be made to write in the form of p by q, are also called as rational numbers. Not necessary that they should look like a fraction, they can also be written in the form of a fraction. And apart from this, even decimals, for example, 1.6 can be written as 16 by 10, or 1.27 can be written as 127 by 100 if we remove the decimal. So again, we are able to represent them as p by q and the denominator is not equal to 0. So these are all the examples of rational numbers. So basically any number that can be written in the form of p by q. Irrational numbers, they cannot be written in the form of p by q, which means then what does irrational numbers constitute? What do they constitute? So root 2, root 3, root 5, root 6. So any non-perfect square number that comes under square root, that we call it as irrational number, because root of 4 would become 2 and that would come under the category of rational. Root of 9 would become 3 and that would come under the category of rational numbers. So the number that is inside the square root should be a non-perfect square. Only then it will be an irrational number. And apart from these numbers, we also have pi. Pi is also an irrational number. Though pi is 22 by 7, it is an approximation. Though it can be written as p by q, we still call it as an irrational number. Now, there is one more stark difference in terms of the distinction between rational numbers and irrational numbers. That is, rational numbers have either a terminating decimal expansion or a non-terminating recurring decimal expansion. A non-terminating recurring. Whereas our irrational numbers have a non-terminating, non-recurring decimal expansion. So this is the main distinction between rational and irrational. For example, if we take a calculator and try to find the value of root 2 or the value of pi, that is 22 by 7, we would get a non-terminating, non-recurring decimal expansion. Whereas any rational number, they'll be giving you either a terminating or a non-terminating recurring decimal expansion. So you can try this out. If you are unsure about the types of decimal expansions, please click the link in the description. You will have I have explained a video on types of decimal expansions. Now we will move on to another concept which is called fundamental theorem of arithmetic. So the fundamental theorem of arithmetic goes like this. If we take any composite number, we will be able to represent it as product of primes. So just a recall of what are prime numbers and composite numbers. Prime numbers are the numbers which can be divisible only by the number itself and 1, whereas composite numbers can be divisible by some other number as well. So, what the fundamental theorem of arithmetic tries to say is any composite number we will be able to express it as product of prime numbers by factorization, which I'll show you in some time. And this factorization is unique in the sense we will get one and only one answer, and the order may differ from one person to the other. Let us try to understand what the fundamental theorem of arithmetic says by solving the first problem. So this is type 1, and here the star represents, the star symbol actually represents that it is of least importance. Two stars will represent medium importance, and three stars will represent a highest level of importance. Importance in the in terms of the examination point of view. So when it comes to 3825, we are going to factorize 3825. Since the number ends with 5, we know it is divisible by 5 table. So now 5 7 times is 35. There is 3 2. 5 6 times is 30. There is 2 5, and again 5 5 times. Again it is divisible by 5. So 5 1 times 26, and then 5 5 times, and then 1 5. So we get 3. Now when we add the digits, 5 plus 1 plus 3, we get 9. So therefore it is divisible by 3. So this gives 3 5 times and 1 times. Again this is divisible by 3. So we get 1 times and 7 times. So we are able to represent 3825, the given number, as product of prime numbers. So that is 5 times 5 into 3 into 3 into 17. So when we write it in short, we write it as 5 square into 3 square into 17. So we should be able to write it in exponential form, exponent form, that is 5 square, 3 square, and so on. So this is very important for the next concept. So what FTA, that is fundamental theorem of arithmetic, says is that we need to understand that this number 3825, we are able to represent it as product of 2 5s, 2 3s, and 117, and the order may differ. For example, if someone else does the same question, they may start with a 3 times table or a 17 times table. So the order may differ, but everyone will get 2 5s and 2 3s and 117 if it is done right. So that is what the theorem says, which is the given composite number can be expressed as the product of primes, and this factorization is unique in the sense everyone will get the same answer, but the order may differ, and it may differ because it is okay if it differs also, because we know that multiplication is commutative. So having said that, it is time for some practice. You may pause the video and try to solve these 3 questions. And please check the answers by pausing the video. Now, as you're solving these questions, if you have any difficulty in terms of understanding what number will divide a particular number, then we need to recall the concept of divisibility tests, about which I have made a separate video, which is also given in the description. Now we go to the next concept, that is finding LCM and HCF. So we need to remember a few key points before we get into the question. That is, HCF can be found as the product of the smallest power of each common prime factor, and LCM is the product of the greatest power of each prime factor. So I'll explain this by solving a problem, and that is our type 2, second type of question. The first type we saw was prime factorization, and now we are going to look at how to find LCM and HCF. So now the verification also is important. HCF times LCM equals product of the two numbers. So this is also something that we need to understand. So let me directly solve this question. So first, if they have given us two numbers, 336 and 54, we need to take the numbers individually and do the prime factorization like how we did it in the first type. So when I factorize, so this can be divisible by 3. So I do 1, 1, 2, and again it ends in 2. So it is divisible by 2. So 2 5 times, and 2 6 times. Again it is divisible by 2. 2 2 times, and 8 times. Again it is divisible by 2, 14, and again it is divisible by 2, 7. So now this 336 can be written as 2 power 4. There are 4 2's here. So 2 power 4 times 3 times 7. Likewise, I'm going to factorize 54. 5 plus 4, 9. So it will be divisible by 3. So 3 1 times and 8 times. Again 3 6 times. Again 3 2 times. So we're able to write 54 as 3 cube times 2. So once we have written it in this form, we need to now get back to the concept. So as given in this hint above, we know that HCF is nothing but the smallest power of each common prime factor. This means that we should take only the common prime factors. So when we compare the two values, um, we can see that the common numbers are basically, here we can see 2 is common and 3 is common. 3 and 2 are common. 7 is not present in the other, that is the prime factorization of 54. So now we just write them once. We write 2 ones and 3 ones. And now we go back to the hint that is given at the top of the screen. Product of the smallest power of each common prime factor. So we took the common factors in both these prime factorization. In this as well as this, we took the common prime factors. And now we have to do the smallest power. So when we compare 2 power 4 and 2 power 1, we know that 2 power 1 is the smallest. When we compare 3 power 1 and 3 power 3, we know that 3 power 1 is the smallest. So when we multiply these two, we get the HCF value as 6. That's how we solve the HCF. When it comes to LCM, we should not take the common numbers, but all the numbers. And as you can see in the screen, this word common at the top has been mentioned only for HCF. For LCM, we have to take all the prime factors, which means 2 comes once, 3 comes once, and 7 comes once. So we take all the prime factors and then we go for the greatest power in each of them. So when we compare 2 power 1 and 2 power 4, 2 power 4 is the greatest. When we compare 3 power 1 and 3 power 3, 3 power 3 is the greatest. And 7 has just only one number, so that we multiply. So when we multiply these three, we get 3024. Now, how do we verify? So verification is an important part. So what we do is, you can see here, we have mentioned about verification. In order to verify whether the answers that we have got is right, we need to take left hand side and right hand side. So the left hand side will be, as mentioned, HCF times LCM. We need to multiply the answers that we have got. And the right hand side will be product of the two given numbers. So the HCF that we have got is 6 times the LCM that we have got is 3024. When we multiply these two, we get 18144. Whereas in the right hand side, that is the product of the given numbers, 336 times 54. This also we'll get it as 18144. So this equality says that we have done the problem right. One most important thing to understand is that this need not hold good for three numbers or more. It always holds good for two numbers. But in the question, if they have given three numbers, the same verification need not hold good except for a few situations. A question may arise: what if there is no common factor at all, because in HCF we're taking the common factors. When there are no common factors, then the HCF will be 1 and the LCM will be the product of the numbers. We will get a question like that. We'll get to it shortly. Now it is practice time. You may pause the video and try these 3 problems. Now it's the answers time. You can see these are the answers. And so this part C was given intentionally, because as I said in the previous part, when 3 numbers are given, usually the verification doesn't hold good. But here in this problem, the verification holds good because the 3 numbers are coprimes. So that brings me to the question of what are coprimes. When the numbers have the highest common factor as 1, that is, they don't have any other common factor apart from 1, then we call them as coprimes. The idea of coprimes will be used in the second exercise. So now we can see these are all the answers, and quite rarely we have got the verification as same even for 3 numbers, but usually when we take 3 numbers together, the verification doesn't come out the same. It holds good only for 2 given numbers. We move on to the next type of question, that is the type 3. When HCF is given and we are asked to find LCM or vice versa, then how do we solve? As you can see, it's a 3-star question, which means it's very important from examination point of view. So as you can see, they have given the HCF as 9 and we have to find the LCM of the 2 given numbers. Now the given numbers are 306 and 657. We know how we can find LCM from the previous concept, that is, we prime factorize and then we write the factors, and then we do take all the factors and we take the highest powers. But that is not how we are going to do it here, because the value of HCF has been given. We are going to directly solve this problem using the verification step. So we know that HCF times LCM is product of the given numbers. This is something we know. So now HCF is 9, LCM is what we need to find out. The product of numbers is 306 times 657. Now LCM equals 306 times 657 divided by 9. The 9 in the left hand side is in multiplication, so when it comes to the right hand side, it becomes division. So now we can cancel this 9 3 times and then 9 4 times. Now when we multiply these two, we get 22338, and this is the LCM for this answer, for this question. Now I would like to bring our attention to a particular thing, which is the same question can be approached like how we did previously, like taking factorization and everything. But if they ask this in a 1 mark or a 2 mark question, then we would not have so much time to factorize. So we use whatever is given in the question, that is the HCF value is given. So let us make use of it and directly solve it using the verification step, which is HCF times LCM equals product of the 2 given numbers. And I would also like to bring our attention to one part where it is better to cancel this 9 with 306 in this step instead of multiplying the numerator and then dividing it. So let us make it simple by cancelling the 306 with 9 and then multiplying. That way we can also conserve some more time. Next is the 4th type of question. The 4th type of question is we need to check whether the number 6 power n can end with the digit 0 for any natural number n. So now, and this is a 2-star question of medium importance, and it's a 2-mark question as mentioned. So let us try to understand something. The question is whether 6 power n can end with the digit 0. for any natural number n, which means n can take the values of 1, 2, 3, and so on. Now, I'm just explaining certain things in the rough column. The question is 6 power n. If we substitute 6 power 1, we get 6. If we substitute 6 power 2, we get 36. If we substitute 6 power 3, we would get 216. So in this way, if we substitute any value in the place of n, will the number end with 0? That is the question. So let's try to understand the question this way. So even if we write 6 power 10 or 6 power 27, at any point in the series, will it end with the digit 0 is the question. Now, bringing our attention back to another concept. If a number ends with the digit 0, say for example 20, then for sure the number will be having the factors 2 and 5 at least once. As you can see here, it will have the factors 2 and 5 at least once. So now what do we write is 6 power n. The only factors of 6 are 2 and 3. So 6 power n can be written in the form of 2 times 3. But as I told you over here, we know that if a number has to end with the digit 0, it should have the factors 2 and 5 at least once. But as you can see here, 6 has only the factors 2 and 3. 5 is not present here. Since 5 is missing, we can very well say that 6 power n can never end with the digit 0. So we can also take the help of the uniqueness of fundamental theorem of arithmetic, and we can say that it will never end with the digit 0. So we just write this expression 6 power n equals 2 times 3 and then whole power n. So here we can say that 2 is present, but 5 is not present. The factor 5 is not present. And we know that for it to end with the digit 0, it should have both the factors 2 and 5. It should have both the factors. That is, for this number to end with 0, it should have both 2 and 5 as factors. But here only 2 is the factor. Hence, we can say that the given number, that is 6 power n, will not end with 0 for any value of n. And we can also mention the fundamental theorem of arithmetic. So why do we take fundamental theorem of arithmetic here is because a question may arise that, because I solved and I got 2 and 3, if someone else solves, they may get a different answer. But that is not the case, and that is what exactly our fundamental theorem of arithmetic says. It says that everybody will get the same set of factors, the order may differ. So we bring in the uniqueness of fundamental theorem of arithmetic, we take that as a statement, and also we explain this. Likewise, let us get into type 5. Explain why this expression is a composite number. Now, anytime when they give an expression like this and ask a question like this, the previous type and this type are standard questions. Like these cannot be manipulated so much. So these questions will have one number that has been repeated. As you can see here, 7 times 11 times 13 plus 13. Now, I would like to bring our attention to the question. If it was just 7 times 11 times 13 without a plus sign, we can right away finish the answer by saying it is a product of prime numbers, therefore it is composite according to the fundamental theorem of arithmetic. That is what the fundamental theorem says, that product of primes is composite. So we just mention it, but here the plus sign is an issue. We have a positive sign, that is an issue. The fundamental theorem says only about product, it doesn't say about sum. So, but in such questions, there will be one number that is repeated. So that number needs to be taken as common out. So in that numbers place, we will have 1. And here also we have 1. In both these places, we write 1 because that has been taken common. 13 has been taken common. Now we multiply the rest. We multiply these. We get 77 plus 1. Now we get 13 times 78. Now 13 is a prime number, but 78 is a composite number. So we factorize 78. And then we get another 13 here. There is already a 13. So we get 2 times, 3 times 13. So now we would be able to represent it as 2 times 3 times 13 square. And we can see that these are all just product. The plus sign in the question has been changed. So now we have only product and all the numbers are prime numbers. So therefore we conclude by writing so we conclude by writing these are product of primes, and hence the given expression is composite. And we can also mention the fundamental theorem of arithmetic, because that is what guarantees this idea. So the fundamental theorem of arithmetic basically says, I'm recalling it again, product of primes is composite. So we have got the expression as product of primes, therefore it should be composite. And now we go on to the last type of question, that is statement problems. So these are of medium importance. They can be asked in 3 marks or mostly case-based questions. Please pause the video to read the question once. Yeah. So as you can see, the question talks about two people who are going on a circular path in a sports field, going around a circular path. Now Sonia takes 18 minutes to finish one round, and Ravi takes 12 minutes to finish one round. Now the question is, if they keep going in this round, there will be a point where Ravi will overtake Sonia. At what point will they meet again? So that is what is the question about. So because Ravi is running faster, he takes lesser time, which means he's running faster. Sonia takes slower. She runs slower. But at some point, they'll meet at the starting point. When is this? Is the question. Now, when it comes to approaching numericals, that is statement problems, usually the hint that some of us might assume is maximum or minimum. Such keywords will equate to finding out whether it's HCF or LCM. That is true to an extent. For example, in the question, we find the keyword maximum. If we find the keyword maximum, or if we find the keyword most or highest, then it equates that we need to find HCF. And if it contains words like minimum or least, then we need to find the LCM. But this may not work always. So I would like to bring our attention to a different concept that can be applied over here. So the previous sums that we did in this video, and there was one observation to which I would like to bring our attention to. In all the numericals, we would find that the value of HCF will be lower than the two given numbers, and the value of LCM would be higher than the two given numbers. I would like to show you an example. Just a few slides before we saw this. So as you can see here, the value of HCF is less than the two given numbers. It is less than 336 and 54. the value of LCM will be more than the two given numbers. This is something we need to remember. So as we remember that, I would like to bring our attention back to this question. Now, logically speaking, what we are going to find is when they will meet next. So the time they will meet next, will it be less than the individual values 18 and 12, or will it be more? Yeah, you're right. It will be more than 18 and 12 because they cannot meet less than 18 minutes or less than 12 minutes because they'll be just completing one round in the circular ground. So therefore, what we are supposed to find will be a higher value than 18 and 12, which means we need to find the value of LCM. So that can also be one way of looking at this question. So we need to find the value of LCM. And as you know, it can also be a recall. We need to factorize 18, which is 2 9 times, 3 3 times, and factorize 12, which is 2 6 times and 2 3 times. So now 18 can be written as 2 times 3 square, and 12 can be written as 2 square times 3. And if you would remember how to find LCM, it was just taking all the numbers at once and the highest powers. So this will give us 4 times 9, which is 36 minutes. So we would conclude by saying that Ravi and Sonia will meet after 36 minutes at the starting point. And for numericals which involve statement sums, we need to conclude by writing it as a statement. So we write Ravi and Sonia will meet after 36 minutes. For some of you who are able to understand with reference to this, please feel free to go ahead, because sometimes maximum or most means HCF and minimum or least means LCM. That works really good. But also in questions like this where neither of these keywords have been mentioned, then we need to get to this logic of what are we supposed to find. Is the number that we are intending to find less than the two given numbers? Then it's HCF. If it's more than the two given numbers, then it is LCM. And our final set of practice questions, please pause the video and try solving these questions. Yeah, and these are the answers. You can pause the video and check the answers. I would also like to say that the last question, the army contingent, they have used the keyword maximum, which means that obviously says that we need to find the HCF. But at the same time, we can also understand that if they need to stand, if these two need to stand in the number of columns, then the number of columns cannot exceed this value 616 and 32. It has to be less than these two values. So therefore we find HCF. So that way also we can remember this. So that brings me to the end of exercise 1.1. So I hope you understood the concepts, and if you have any questions, please drop them down in the comment section, and feel free to follow this page and for further videos on the subsequent chapters. And if you would like to for me to post a video on any particular concept, please drop a message of that as well. Thank you so much.